The invariance of electric charge. To a stationary observer, the electrical charge of an electron is the same in all reference frames. It does not care about directions in space-time. It is a physical constant. Electrical charge is invariant under change of velocity. The amount of it does not dilate or contract with change of velocity. Atoms are comprised of a positively charged nucleus and negatively charged electrons that orbit the nucleus. Atoms are, when not ionized, electrically neutral, as we can easily observe in the macroscopic world. Because electrons and protons move at different and varying speeds in and around the nucleus, atoms can be consistently electrically neutral only if electric charge is the same at all velocities. Further, we observe that an ionized atom does not become more or less ionized when moving than when stationary, and rapidly moving electrons are not more or less charged than slowly moving electrons. When a positron and an electron collide, head on is simplest, but any collision will do and annihilate each other. They produce electrically neutral photons. Such an event can be seen from different reference frames. If electric charge varied with velocity, then unless the electron and the positron were moving together, the resulting photons could not be electrically neutral, or in such cases, we would not have conservation of electric charge. We can take the view that conservation of electrical charge compels electrical charge to be invariant under change of velocity. It would be a most strange universe if electric charge was not invariant under change of velocity. Why should electrical charge be a Lorentz invariant? Mass is not a Lorentz invariance, although rest mass is invariant. There is another difference between mass and electric charge. If we add a proton to a neutron, the resulting nucleus has a mass that is not equal to the sum of the masses of the two constituent particles because of the binding energy holding them together. If we put two electrons together, the resultant nucleus has an exactly equal amount of electric charge as the two constituent particles. We do not know why electrical charge is invariant under change of velocity. It is as if electrical phenomena are not part of space-time, or do not happen in space-time, or are not connected to the space-time, or do not feel direction in space-time. We say that electrical charge does not couple to space-time. Charge density, which is the amount of electrical charge in a given volume of space, is not Lorentz invariant. That's quite important. I think I will say it again. Charge density is not Lorentz invariant because the stationary observer sees the length of a moving volume contract in the direction of the motion. She sees the actual volume contract. For a moving volume, we have volume equals to length into height into width. Volume prime is equals to L prime into H prime into W prime. That is L prime times H naught times W naught. That is root under 1 minus V square L0 H0 W0. That is volume 0 times root under 1 minus V square. Charge density is charge divided by volume, and so we see that a stationary observer will see the charge density of a moving volume to be greater than the charge density of the volume when stationary. Greater charge density means greater electromagnetic force per unit volume or length. Magnetic effects. Consider a stationary wire with no electrical charge but carrying a current. An electrically charged body moving parallel to the wire at velocity v feels a magnetic force attracting or repelling according to the direction of the current from the wire. A moving charged body is a current just as much as moving electrons are a current. However, to an observer also moving at velocity v, the electrically charged body is stationary and therefore should not feel a magnetic force from the wire. Nonetheless, the moving observer must see a force affecting the motion of the charged body. This force, as seen by the moving observer, is not magnetic, it is electrical. Think Lorentz force law. The Lorentz force law is vector F is equals to Q vector E plus Q vector V cross B vector, where V is the velocity through space, not space-time. An observer who moves at a velocity different from the velocity of the charged body will see the magnetic part of this force because the relative velocity between them will not be zero. An observer who moves at the same velocity as the charged body will see vector F is equals to Q times vector E. One observer's magnetic force is another observer's electrostatic force. This is like one observer's time is another observer's space-time. But we would expect that they both observe a force because they will both observe a deflection of the path through space-time or just space of the charged body. The stationary observer sees a magnetic field of magnitude determined by the velocity of the charged body relative to her. The moving observer sees a magnetic force of magnitude that is determined by the velocity of the electric charge relative to him. Because observers in motion relative to each other see the electric charge moving at different velocities, they see different amounts of current and thus see magnetic fields of different magnitudes. If one observer moves at the same velocity as the electric charge, the charged body or the electrons in the wire, then that observer sees zero magnetic field. A stationary current carrying wire is a lot of positively charged ions fixed in a crystal matrix that is stationary and a lot of negatively charged moving electrons flowing along the wire. For the stationary observer, the stationary wire is electrically neutral. Put a stationary electric charge near it, and so the charge density of the positive ions must be equal to the charge density of the moving electrons. Think about it, that the number of electrons per stationary meter length of wire has got to equal number of protons per stationary meter length of the wire. But meter length changes with velocity, length contraction, and so to the stationary observer, the meter of electrons is shorter than the meter of protons. There can be an electrostatic balance only if the density of electrons in the moving meter is less than in the density of protons in the stationary meter. This electrostatic imbalance is apparent to the observer moving with an electrically charged body because in this view the electrons are not moving and thus there are more protons per meter than electrons. This effect is exacerbated by the contraction of the proton meter as seen by the moving observer. Thus the moving observer sees an electrostatic force affecting the stationary in his view charged body, and the stationary observer sees a magnetic force affecting the moving in her view charged body. Yes, it is little different to untangle.